Hello, beautiful people on the internet. This is Tushar. Today is 1st of February. We are finally scaling our work to computer vision, and let's review this paper and get a background for the project that I might be working on this semester. So, yeah. So, you want to work on issues available law. The most elementary part of this. Methods and techniques is for studying the practice has slow and lack precision. Therefore, modern day scientific engineering implementations, computer and machine learning, performance prediction manager. Should make it be challenging to monitor these microscopic organisms. This is actually a how do we highlight? I think this is our approach is to generate a powerful automated Plankton condition system to automate identify them and improve the deep neural network for classification of Plankton holographic imagery created with the data method of data conformity evaluation. The performance of the alien classifier is improved by various hyperparameter tuning and the regularization techniques and the pending metadata conformity evaluation created with the method of data conformity. Our approach is to generate a powerful automated verification system to the performance of the DNA classifier is improved by various hyperparameter tuning, regularization techniques, and pending metadata. Perfect. Conformity evaluation is based on matrix that's calculated on a continuously defined sequence of calculated L1 norm tensor subspace of the conformity evaluation is based on a metric that is calculated continuously defined sequence of calculated L1 norm tensor subspaces of the Plankton images. We know that our classifier performance are calculated where our results improve performances from contemporary deep learning classifier alone. Index terms are autonomous classification, DCNN, data conformity, L1-PCA. Okay. Use it. Use large polygon universities such as ImageNet and emerging high performance graphics processing. Use accelerated adoption of the deep neural networks as means to carry out visual object detection for several applications include gesture recognition, web search, medical and aerial imaging, to name blah, blah, blah. When you data, they often move to the resolution for labels which lead to significant performance degradation. This will be considered new method based on L1 norm principle component analysis to improve the quality of the label data sets that are used for training a custom version of DCNN described in the second image known as mini VGG. We test experimentally the classification accuracy of mini VGG using imagery required for Raman novel submersible microscopic holographic imaging system known as holocam. Okay, so mini VGG is something that we need to look, and then to improve the quality of the label data sets that are used for training a custom version of DCNN described known as mini VGG. We test experimentally the classification accuracy of mini VGG using imagery acquired from novel submersible microscopic holographic imaging system known as holocam. Specifically, we consider a three-way tensor dataset generated from the fixed size of 128 by 128 grayscale subscenes from the holocam images which are pre-categorized into corresponding classes of plankton which are pre-categorized into by the human domain experts. The conformity of the tensor data per class is evaluated through iterative projections on robust high confidence data characterizations per class that are returned by L1 norm tensor subspaces. Non-conforming tensor slabs are likely to be contaminated by excessive noise or non-conforming tensor slabs are likely to be contaminated by excessive noise or examples mislabeled due to mistakes made during the data entry and are automatically removed from the dataset. In this work, we conduct experiments with 4 classes of planktons labeled and each class is contaminated with images of background scenery as well as images of other plankton species, that is yes, and we show that the L1 norm tensor conformity curation of the data identifies and removes inappropriate class instances from the data training set and drastically restores the classification accuracy of many VGG. So, in situ digital imaging technologies are fast emerging as important means of recording spatial and temporal distributions of plankton in the ocean. In particular, digital holography is a promising technique that provides 3D spatial distribution of particles in plankton within a given sample volume. We have obtained a large training data set consisting of subscenes of holographic imagery captured in situ using the holocam, a submersible digital holographic imaging system. So to acquire images, the hologram is lowered into the water. Okay, so these are the these might not be something relevant. Okay, next hologram is reconstructed. Okay, so using the Fresnel diffraction formula at incremental steps of 500 micrometer, resulting in a 70 planes per image, where particles at a particular depth come into focus at the given plane, generating a 3D spatial distribution of particles within a small volume. Finally, a composite flattened image is generated such that every particle in a given hologram is presented at an optimal depth where it is in focus. These 2D images are 2048 by 2058 pixels in size and spatial resolution of 4.9 pixels. Then the tens of thousands of images are processed and reconstructed from these. 4 commonly seen classes of elements are identified either through class, subclass, or species level as coped an unknown thin elongated air. Okay, and both definition within the large flattened images. The holographic image is cropped to 188 by 128, centered on the organism of interest. This process produced 900 images. Okay, the images from the load. Okay, fine. Sample of the unique. Okay, the total 4,278 subscenes that contain these plankton from holograms. Okay, perfect. We test and demonstrate for the first time in the literature the application of the novel tensor data conformity evaluation tools. First in literature application of novel tensor data conformity evaluation tools, that is to improve the training and classification accuracy of CNN for autonomous plankton classification. We access the quality of the labeled plankton images for each of the 4 classes by first calculating the robust subspace representation along each tensor by means of L1 norm tensor PCA. Projecting density on the calculated L1 norm subspaces produce a soft score in the range 0 to 1, which measures the pixel-wise conformity of each tensor. This is the quality of the results for each of the by first calculating row subspaces, projecting the tensor on the calculated row subspaces, and which measures the pixel of each tensor for each class. The conformity of each image is calculated by averaging the pixel-wise conformity along each 2D image with a high score are highlighted as non-conforming, removing inappropriate classes instances from the training set. By thresholding operations lead to improvements in the quality of data, which drastically increases the classification accuracy. Okay, so the conformity of each image is calculated by averaging the pixels conformity each 2D images with a high score are highlighted as non-conforming, removing appropriate class instances from the training set by threshold operations which thus shows the conformity of each. Okay, so basically we need to work on conformity to average. Okay, calculate the conformity of each is calculated by averaging the pixel-wise conformity along each 2D image with a high score. With high score are calculated, which is high score are calculated asserted as the non-conforming removing. Okay, perfect. Okay, threshold wala is that thing. Okay, and then this is the architecture that they're using. 128 by 128 by 132 64, and then fully connected plus reloop, and then softmax. And these are the layers. Convolution layers, activation, batch normalization, convolution, activation, batch normalization, max pooling, dropout, and perfect. Okay. The only thing I didn't understood is this 1x1x65536, but let's see. And then evaluate experimentally the impact of applying tensor conformity evaluation of the hologram data on the classification accuracy of a customized version of VGG. A typical CNN architecture widely used with a computer vision, also known as mini VGG. CNN are a category of neural networks designed for image recognition classification. CNN apply a network of hierarchical filters to the grid of pixels in a manner inspired by Hubble and Weasel experiments of visual cortex, response on visual signal. The filters are then convolved against the input, performing element-wise multiplication between the filters and the region of images that that it occurs for every possible region in the image. Mini VGG has 2 units of conv pool blocks followed by a set of fully connected layers where conv pool and fully connected denotes the convolution. Okay, perfect. Okay, the network layers are shown. The pool block is also known as the max pooling. And okay, so also we have done subsampling or downsampling reduces the dimension of each feature map by picking up the maximum numbers in a 2x2 matrix of feature map. It makes the system invariant to transformation, translations, and distortions. Feature reducing subsampling or downsampling reduces the dimensionality of each. It makes the system okay, perfect. Used to introduce non-linearity to the system. The numerical calculations complexity we've seen this. So we consider a 4-way tensor, a 4 3-way tensor, each containing grayscale subsequences. And our goal is to use a pre-processing tool called data conformity evaluation to find misclassifier analysis. The data conformity evaluation converts the original tensor data into a new tensor of the exact same dimensions, where each new tensor entry measures the conformity of that entry with respect to all the other data points. The conformity matrix will take values from the certain set. This is achieved by utilizing iteratively refined L1 norm, that is absolute error, data subspaces, detection of non-conforming data entries, enables identification of contaminated data slabs with respect to the Cth data tensor. We first unfold the tensor along its column, rearrange the column, creating a data matrix, and we calculate the L1 norm principal component by solving the following maximization problem. The resultant basis describes accurately the subspace spanned by the column of the original tensor that contains nominal data. Columns that are contaminated with anomalous data are not spanned by the resulting basis vector. The conformity of the data column is computed by projecting each column on the calculated subspace. And the conformity values are converted to tensorization, where this stands for an all ones matrix of dimension. Operator converts the matrix. Okay, that is okay. Conformity values corresponding to each column of the tensors. We repeat the process for the rest of the modes in the original data tensor and calculate the conformity tensors. We calculate the final conformity tensor by combining the above calculated tensors in a additive fashion, as well as normalizing the tensors so that each element is in 0 to 1 range. Okay, perfect. And then probability split, basic, the number of samples used. Okay, this is fine. Model tuning is something that is pretty obvious. Model tuning is obvious. And yeah, so the major challenges in pre-processing and the L1-PCA that they are doing to kind of represent the feature space. Yeah, I think I would need to learn more about conformity and like learning more about the math behind this, like how they are calculating the tensors. Rest, the results are definitely promising. Classification error rate and improvement seen on cleaning the contamination, which is 91, 98, 93, 78, and contamination B. Okay, so okay, perfect. So in different conditions, or maybe okay. The first experiment, pure Plankton images, and then mixed classes, I suppose. Okay, perfect. See you in the next video. Take care. Bye bye.